scandals that happen in physics research about how one scientist faked his data and almost won the Nobel Prize. And the video is interesting because it kind of explains almost everything about how physics research works, how you write papers, how publications. So you, besides that story also, you learn a lot of many interesting details. If you are ever interested in doing a graduate study in physics, right, then you see how it works, right? How you write papers, submit peer review, and things like that. So how people check your data. And if for those people who are doing experimental physics, right, I guess from this story you will learn the importance of recording your data, keeping a logbook. So I don't know how is the online lab being handled, but if you're doing experimental physics, the logbook is something that is very important, right? And it's because of stories like this. So it is a good lesson to learn every year. Oh really, Sheldon? Oh, okay, yeah. So that's why, right? So that's why in science, people take very seriously about fake data. And so I guess the lesson that people teach the student, right? Don't bother fake data because this is science. Eventually, it will always be found out, right? Because when people are doing science, the formula is there. Everyone can derive the formula. So if there's a mistake, everyone can find it, and things like that. So the moral of the story, right? Do not fake data. Okay, so we have quite a few presentations today, and like I said, since a few of you have prepared the same question, I guess just present, right? I think it's fine. Always, yeah, because the main point is just to practice our presentation skill. So, but before we do that, we'll do that after the break. So for now, we shall continue on to solve another potential energy system, which is a free particle. So did I start recording? Hang on. Yes, I did, and I did here. Okay. I heard. Okay, so it is the problem that I want to solve today is a free particle. And the previous class was the potential well. I think if you have taken Prop 1 class, you have kind of mentioned, he has mentioned potential well already, right? So we did that last week. I don't know if we covered free particle in modern physics, but we will cover this now. Okay, so what is a free particle is exactly what you mean by in mechanics. It means that a particle has no force. Okay, so it has no force. That means if the force is 0, the potential energy is going to be constant. So to make it simple, we'll just say that our potential energy is a 0. Okay, so free particle means in mechanics, well, no need to write mechanics. So let's just say a free particle, right? 0 force acting on it. Okay, so therefore, what is my potential energy function? So therefore, we consider the potential, energy function to be very simple. Potential energy function is, we choose a function to solve, right? And here is just 0. And it is 0 for all x from infinity to negative infinity to positive infinity. So this kind of almost like makes the Schrödinger equation very easy to solve. But as we will see later, there's going to be some trickiness involved, even though the problem seems to be very simple. So let's just solve the Schrödinger equation, right? So the time-independent Schrödinger equation for this potential is what? So I no need to remind, yeah, I'm lazy to write down the Schrödinger equation, but I guess you know the equation already, right? It's plus v times psi, but here is 0, so there's nothing here. Plus 0 and it's equals to e times psi. Okay, so the small psi is the eigenstate of the Hamiltonian. Remember, the time-independent Schrödinger equation is where we want to find the eigenstates of the Hamiltonian. So this becomes a straightforward differential equation. So this is the second derivative x is equal to negative 2me over h bar square and psi. And this is an equation that is, we don't need to consider region 1, 2, 3 like in the potential well, because this is for everything. So this, the potential energy function is 0 everywhere. Oh, I forgot to mention also, let's assume E is positive. The energy is a positive number. So every constant here are positive, and there's a negative sign over here. Okay? Is it lag? Oh, transformer voice. Hang on. Wait, test. Yeah, Monday. Happens on Monday all the time, right? Testing, 1, 2, 3. Testing, 1, 2, 3. How about now? Let's give it some moment to settle down. For me, my internet seems fine lah. Even playing YouTube video was smooth.
Processing. The techniques they invented back in the telephone.
Where's my OBS? Test. Yep. Sometimes freeze, sometimes speed up. Oh, yeah, I guess it's the internet problem. I think so. If it's like that, it probably means the internet problem, right? Not our computer. So I guess we can't do much about it. This is why we have recording. So don't worry. Okay, let's continue first. Let me adjust the brightness a bit. So yeah, just this is a differential equation that we want to solve for the case of the this the Schrodinger equation becomes like this. Okay, so it's the second derivative negative constant times psi. So we have the general solution. Yeah, Malaysian internet is not that good, unfortunately. Okay, so the psi of x, we have the general solution. Everyone knows how to solve. We got a constant e ikx, right? And then plus another constant e, and then there's a negative ikx. So these are two linearly independent solutions, and the k is of course I think everyone has learned this in ODE already, and we have used this several times already. It is square root of 2me over h bar. So k is a real number because e is taken to be positive. Okay, so this is the problem that we want to solve over here. And in fact, right, we can also get the expression for e. So if I solve this for e, right, how do I get e? Well, e is, if I square both sides, is equals to k squared h bar squared over 2m. Okay, so this is my formula for e. Okay, so this is my solution already. So let's try to get the full wave function, including the time dependence. So the full wave function, time dependent wave function is, well, remember how did we get the time dependent wave function is psi of xt, right? And we arrive at the time independent Schrodinger equation is because we have been using separation of variables. So my wave function x of t is just this function times this function, and we have already solved this function some time ago. For any potential, it's just iet over h bar, and then the psi of x is, well, it's over here, right? So it's aeikx plus be minus ikx. Okay, and this e here is the same. So this e we have already found. So let's just put this in, right? And then I'll multiply this inside. So what we have here is that we have a plane wave solution. So we got a times e to the power of multiply everything inside. So I got I. Well, both have I. So let's put the I outside, and then I got a kx minus Et over h bar. So E over h bar, if I divide this down, it becomes k square h bar to the power 1, right? Divided by 2m. And then there's a t, don't forget the t over here. Okay, so everything is correct. We can check. And then the same thing for the second term. So I got b e to the power of I. Well, I, so there's a negative, so let me put the negative outside. This is also negative, so it will become kx plus, replace everything the same, so k square h bar over 2m, and then times the t over here. Okay, so now this one looks like a solution to the wave equation, am I right? So it looks like the so this is a wave equation. If, like I said, we have since mechanics and electromagnetism, we have encountered waves several times already. It will be more clear if I'm going to call the whole thing as omega. So if I let omega is k squared h bar over 2m, then my solution becomes this. So psi of xt is equals to a e I kx minus omega t, and then I got plus b e negative I kx plus omega t, right? So this omega is a positive number. So from here we see that this is a wave function, right? So this is why we got quantum mechanics, it corresponds to the wave function in the same reason as because we got the same wave equation. If you recall what we did from electromagnetism and mechanics, that if I got a kx omega t, this is a wave that is traveling towards the positive x direction. So it's the wave traveling to the right. So this is a function where the wave is like going to the right. Then if I have kx plus omega t, right, so this is a wave traveling to the left, right? So it's something that is going this way. So these are actually two separate solutions, and when we are solving the time independent Schrodinger equation, we just like we are finding individual eigenstates of the wave function. So in order to simplify, right, what I will do is I will simplify. Okay, so that means instead of writing two terms, I'll just write one, and k can be positive or negative. Okay, so this is for if it's traveling to the right for k positive in both cases, right? So if k positive, these two have the same sign, it will make it move to the left. Okay, but if k is negative, then I can change the direction. So what I'm going to do is just write one term, and then allow k to be positive or negative. In other words, what was my k? It was square root 2me over h bar, and then it can be positive or negative, right? So that my solution now becomes what? So x and t, and then it's just one term, e I kx minus omega t. Okay, so k can be positive or negative because of this, and also my omega was given by this. Okay, so let's write out everything. So I got omega is equals to k squared h bar over 2m, and then k is plus and minus 2me square root over h bar, so that in whether k is positive or negative, I can actually calculate my energy. My E is equals to k squared h bar over 2m, right? So k squared h bar square over 2m. Okay, so then you notice we can recover some familiar results based on this already. So yeah, now I'm worried about the internet. So everything is fine now, right? I hope. Oh, so Zuri knows Johor. Yeah, so if we get to come back to physical class, then you guys can come to Malaysia, and you will definitely learn more Malay words. right? If you go to mamak shop, you know, order Malay food and things like that, that is where you learn a lot of Malay words. Where were we now? Yes, we were supposed to recovering some familiar results. So the familiar result I'm talking about is the stuff that I mentioned earlier in chapter 1. So notice that my omega, right, is k square. Let's look at E. The E is k square h bar square over 2m. So this is, and omega is 1 less h. So we see something interesting. It is k square h bar over 2m. This is h bar. So this thing was omega. Then we have found that E is equals to h bar omega, right? And what was h bar omega? It is h bar was back to my traditional Planck constant is h over 2 pi, and then omega is 2 pi f. So I got hf. So this is Planck's formula. Okay, and then and what else can we recover? We can recover the de Broglie formula. De Broglie formula is because this is a free particle, right? Free particle. The energy is just the kinetic energy, and my potential energy is 0. Okay, so my energy is given by only just kinetic energy. And what is the kinetic energy here? It is, we can't use half mv squared in quantum mechanics because there is, what is the velocity of a wave? We can't really define it, but we can do p squared over 2m. Okay, so we got p squared over 2m, and well, we do have a formula for E. So my E is this formula. So let's k squared h bar squared over 2m. And then I can simplify this formula, and we realize that P is just h bar k, right? And what was h bar k? H bar k was, back to our traditional notation, k is the wave number. Wave number is 2 pi over lambda. So we have found that P is equals to h over lambda. So this is the de Broglie formula, right? So this is not surprising when we recover this, is because if you recall the traditional quantum experiments, the photoelectric effect, and then the wave-particle duality, right? Those were talking about the photons traveling and then hitting an object. So those are free particle cases, right? Electron interference also, they are free particle passing through the slit. They're still a free particle. So that is why we reproduce all this situation, and now we recognize that they correspond to the free particle solution of the Schrödinger equation, right, over here. Well, over here. So this is the form that we are interested in. Okay, so it looks very simple, but that is where the traditional results and the classical results of quantum mechanics come in. Well, not classical, but the well-known results. No, not necessary. So it's something that I'm not covering, but if you read Griffith's textbook, right, the you can kind of approximate the particle velocity as twice or half of the wave velocity. I forgot. It is discussed in the Griffith textbook. Okay, so the wave velocity is not exactly the particle velocity, not precisely, right? There's a extra factor of 2 there. So you can get the velocity if you want, but you can also use the theorem that the expectation value is you can use this formula. Basically what I mean is P is equals to m dx dt. You can use this to define the velocity as well. So there are so many different ways to get the velocity, right? And it is not exactly the same thing. So the wave velocity is a velocity, but we do not interpret that as when we use the wave particle duality and change it back to particle, it's not the same velocity. This is more closer to link the quantum velocity to the mechanics velocity. So Newtonian velocity. Yeah. Okay, so but I guess to make it simple, we don't need to worry about velocity if we are using wave function, because it could mean this or it could mean wave velocity, and usually we tend to stick to the wave velocity over here. Okay, so yeah, we have recovered all the familiar results, but I said that the free particle case was tricky. Why? Here is a problem. We can't normalize this solution, right? So let's try to see what happens if we try to normalize it. Okay, so if I want to normalize a wave function, right, in a position representation, the wave function square is supposed to be the PDF, right? Again, I forgot, what was it? Probability density function, right? And if it's a probability, then the area under this should be equal to 1. Okay, and I claim that after solving this, it was my solution. So does this, if I modular square this, I try to get the probability, and it's going to be infinity. Okay, so if you can't already see this, I will work it out, right? The meaning of modular square is, remember, it's not just a simple square. It's taking the complex conjugate multiply by itself, the original one. So the complex conjugate of my wave function is just a complex conjugate of the constant, and then e to the power of I, well, there's only one I over here. All these are real numbers. So complex conjugate, it becomes negative I, kx minus omega t. And then this part is just the original one. So it's just I kx minus omega t. And I'm integrating with respect to dx. But if I do this, right, these are exponential I. So exponential I complex conjugate, you just cancel each other. It times becomes 1. And this is a times a. It is a constant. Right? So if it's a constant, then yeah, basically I'm just integrating from negative into infinity to infinity, and then it's infinity. So I cannot normalize, right? So I can't normalize. You, no matter what value you choose, you can't do this, right? So the area under the curve is always infinity. So this is a problem. Okay, and how do we solve this problem? So so let me write the problem first. What we are solving here, right, is actually the wave function. When we solve the Schrodinger equation, we do have a wave function, but what we are kind of assuming is this is for a single k, right? So what we're having here is that a particle wave function of a single k, right? And I just like focusing on 1k only. Just now we have two waves, and then I just reduce to 1k. If it's k positive, that means it's a wave moving to the right. If k is negative, it's a wave moving to the left. So no matter what, we are just looking at a single value of k. But if we are focusing on the single value of k, we encounter this problem. Okay, so in the spirit of Taoxian, this is to remind us that we have a problem here. So how do we solve this problem? Well, we did this for the single k. The good thing about this is we can solve this problem thanks to superposition. So we have discussed superposition in the previous class, is that a wave function plus another wave function is still a solution to Schrodinger equation, right? So this one we cannot normalize, so we cannot really use this as a complete solution. But maybe if I take a k superposed with another k, right, and if I superpose the solutions in the right way, maybe I am able to create a solution that is normalizable. So I don't know if you understand what I'm saying. So I think it will be clear if I start to draw pictures, right? So if I consider a single k, right? So my wave function is a e I kx minus omega t. And remember, what was this? This is just the Euler formula. It is just is basically just cosine. So cosine kx minus omega t and I sine kx minus omega t, right? So it's a sine plus cosine function. Okay, so when I draw picture, I'm only able to draw the real part, and in any case, the k, right, is 2 pi over lambda, and that is the wavelength. So if I plot the graph, right, so if I plot the graph, then my wave function square is just going to be cos square. No, it's a constant, right? It's a constant. But in any case, let me draw one of the parts only, okay, the real part. So the real part of my wave function, if I plot this, then I will get, it's basically a cosine function, right? I know everyone knows this already, but it will be clear when I combine several ones. So this is for a single k, and if I do the modulus square, right, it's just a constant. So the area under the graph, as we have seen, is basically the reason why it's infinity is because we are taking the area under the graph all the way from, it's an infinite strip, so the area is infinity. That's why we can't normalize this. But if I superpose different k, superpose waves of different k, various k, and remember k is 2 pi over lambda, what's going to happen? So let's suppose some random pictures I'm going to draw is like, okay, some wave function like this, okay, and then if I take another solution, lambda 2, okay, so maybe it's a higher, shorter wavelength, right, and then k3, lambda 3 is, maybe this is a very long wavelength. Okay, so if I take psi 1 here, psi 2 here, and then the psi 3 here, if I take psi 1 plus psi 2 plus psi 3, and if I choose them correctly, it is possible to produce a function that psi 1 plus psi 2 plus psi 3 plus, such that to get the final total superposition, it is able to create a wave function that is somewhat normalizable. Okay, so this is what we call the wave packet, and we got the cover page of our lecture notes and also this Teams page, right? And this is what we meant by the superposition. So this is our wave packet. Okay, so this is how we can we can almost see from the wave description to recover the particle description, because if the wave packet is narrow enough, right, then yeah, if this is the real part of my wave function, then if I plot my absolute value square, it is going to be something like this, right, something like this. Right, so the probability of finding the area under this curve is going to be equals to 1 if I'm able to superpose this correctly. Okay, so the key point that we want to do here is that in order to create a normalizable solution, 1k cannot be normalized, but if I sum this up, if I add these functions up in such the right way, how is the right way? Actually, you learn this in math and Fourier analysis, but for now, just trust me, right? There is a way to add the functions up such that this graph plus this graph plus this graph and some other combination of the graph, it will create a wave packet solution. And the wave packet solution, the area under the graph is not infinity. Then this is how we can create a normalizable solution. Okay, so does that make sense? Okay, so let's see. Oh, yeah, about this, right? Your question, equations, kinetic energy. This is why we say that the kinetic energy cannot be defined using half mv squared, right? So the Ke right? The k is, we cannot use half mv square because v doesn't make sense, but we can do p squared over 2m. Okay, so this is my kinetic energy here. Okay, so we forget about the velocity. We pretend the velocity doesn't exist. We purposely express everything in terms of momentum. Momentum is a Hermitian operator in quantum mechanics, so everything works fine when we are talking about the quantum mechanics. And it's because we use this definition, right? We recover the de Broglie formula. So this is a chicken and egg situation, but you can sort of see, if you assume de Broglie formula, then you can work backwards to say this is how we define the momentum, and this eventually this will become the momentum operator, right? Or if you are more comfortable by assuming the momentum operator, then we derive the de Broglie formula, and vice versa. So these are the various ways we can do that. Okay. So I hope everyone is okay with this, because especially for the math people, I did not show this rigorously. I believe you will, for the math students, right? I believe you will learn this in the mathematical analysis, I think. I'm not sure. In calculus, you kind of see something similar to this already in calculus. Actually, calculus 2, you did learn Fourier series, right? For the BSc calculus 2. So what I meant here is I should write down. So these are the situation I'm drawing in pictures. So what we are saying here is superposition of the wave function of various k can produce normalizable solutions. Okay, so superposition was what? Well, I'll just write all this here in terms of equation, and when I sum this up, right, when I draw pictures, I can only draw the discrete differences in k, but remember k is a continuous variable, so I'm actually sum this up of my wave function for different coefficients and different ikx minus omega t, right? So in this case, this is like a sum, and this is the coefficients. Okay, so remember that my k are continuous. So for continuous k, the sum should be actually a integral, right? So this is like a integral, so dk from infinity to infinity, and then so this, my sum will become this, right? And then my coefficients, so coefficient are the okay, I got disconnected. Yeah, I'm back though. So this one definitely I heard the ringtone, and the screen told me that I'm disconnected, and it will auto reconnect me back. Everyone's here, right? Yeah, let me adjust the brightness again. It's too bright. So I was here. Okay. So by the way, you know, if this is lag and you can't understand the live class, and if you have to watch the video, right, I believe the Teams recording will also record the lag, if I'm not wrong. So if there's a lag, then you go to the OBS version to watch the video. So so now I'm very glad I record double backups, so that is a good thing. Actually, that makes sense. Yeah, like a lot of Monday is like a start of the week, so a lot of class going like simultaneously. So this one is the Lim Tao Shen, right? Yeah, that's why I purposely do this. I was reminded of this. So if the internet is running smooth now, I shall talk. Where were we just now? So I want to superpose different solutions in order to produce a wave packet. So it is a sum of different k. But k actually is not a discrete number. K can be anything. So if I sum up a continuous possibility of k, it is like an integration, right? Like a Riemann sum. So so the coefficients will be another constants here, but they depend on k, right? So some stuff that depend on k. And then I got e to the I kx minus omega t. Okay, so this function that depends on k, I'm going to let this to be equal to 1 over 2 pi, and something that depends on k is a function of k. So I shall write it in this way. So in other words, my superposition wave function is going to look like this: 1 over 2 pi integral from infinity to infinity, integrating with respect to k, right? It is my habit to write the dk in front. It is the function of k, and then e to the I kx minus omega t. Okay, so this is my superposition of k. So, and hopefully we try to make sure this is normalizable. Okay. Okay, what time are we at now? So in other words, we got this solution, right? So this is a general solution. This is a general solution for a free particle, and it is a superposition of, remember what was the EIKX? We obtained them from solving this time independent Schrodinger equation. So we created this by superposition of the H eigenstates of various k. Okay, so this is why we want to find eigenstates, because once we find eigenstates, we can do superposition to create new solutions. And it is like necessary and unavoidable here, because just one eigenstate alone, we cannot describe a free particle. It's not normalizable. So what we did was we have to superpose different eigenstates to create a sensible wave function that is normalizable. Okay, so yeah, so that is basically the main idea for this. This is the general solution, but how do we actually, like describe a working solution? So let's consider the solution at time 0, right? So let's consider the initial condition. The initial condition. Okay, so initial condition means the wave function at time 0. Okay, so if I just plug in t equals to 0, what do I get? So I have put the factor of square root 2 pi outside purposely. The reason why it will be clear later. And it is the integral over dk, and then it is a function of k, and I got e to the power of ikx. Okay, so what does this mean? So this one, if you have learned in your calculus or your mathematical analysis, this is actually a Fourier transform. Okay, so So this is the wave function at the initial time. So the wave function at initial time is supposed to be a function of x, right? So at a fixed t. So at fixed t is just going to be some function of x. So if it's a function of x, so I'll just write this as f of x. So should I write big F or small f? Let's write small f. F of x is, according to this equation, this is from infinity to infinity, dk f of k e to the power of ikx. Okay, so I think let's write big F. So big F. Okay, so the big F is over here. So what is actually happening here is I am describing a wave function at t equals to 0. So at t equals to 0 is going to be some function of x. So this is the wave function at time equals to 0, and this fk is an unknown, right? So what is happening here is that, well, how do I actually write down the solution? This is very arbitrary and abstract, right? In order to describe the solution, I say I wanted to have the superposition, and superposition depends on this unknown coefficient. I don't know what are these values. I just put this as something that depends on k. So this part at the moment is still unknown. Okay, so it's still unknown at the moment. So how am I supposed to describe my wave function at time at any arbitrary time? We can fix this. We can determine if we know the wave function at time 0. Okay, so usually we know this because it is given. Or prepared by us. Okay, so it is something that we chose, right? It is an initial condition. Okay, so what happens is, okay, what happens at time 0 is we got this, right? So let me write this equation one more time to make it more clear. It is 1 over 2 pi square root integral from infinity to infinity with respect to dk fk e to the ikx. And the reason why we can know this is because this is a Fourier transform of this. Okay, so just to write down the strategy, I'll continue to write down the strategy. If, right, so if we can figure out fk, then we will know the full solution. We know the full solution of psi xt. It is 1 over 2 pi integral from infinity to infinity dk f k e to the power of ikx minus omega t. Okay, so this was the full solution. If we know this, then in principle this integral is known. Okay, but right now we don't know this. Okay, but what we do know is, suppose that we have some initial condition. So let's call this equation 1, right? I can actually, given this equation, I can actually solve this equation to determine equation 1. And again, it is using a bit of a math theorem. So I'll just state the theorem. There is a theorem which is called the, how to spell its name? Blancharel's theorem. Okay, which is to say that given equation 1, the fk can be solved by this formula. It is very simple. It is just 1 over 2 pi and from infinity to infinity dk fx, and then invert this, so it's negative ikx. Okay, so we got this formula, right? So that is very interesting. So this one is the initial wave function. time 0. Okay, so this one is given. So let's say the wave function is initially some shape, so you know this function, and then to determine what happens later, I need the fk. So to get the fk, well, I need to perform this calculation, solve for fk. Once you solve the fk, I plug this in, and then I got the full solution, right? So the full solution, the wave function at any time greater than 0 is then given by, let me copy this down again. Right, so I'm repeating a bit because I don't know whether it's obvious or not clear, but just in case it's not clear, I can see why it could be not clear, because it is almost like a chicken and egg kind of thing, right? I start with this equation, I plug in time 0, and then I got fx, and then by Plancher's theorem, this actually going backwards, I got this, and with this solution, whatever this is, you perform the integral, you can plug this back in to get your solution. Okay, so yeah, I can kind of understand if this is confusing, because it is like asking who comes first, the chicken is first or the egg first, right? So it is almost like a chicken egg situation, but it is well defined. We are skipping a lot of the mathematical details, and we are just believing and trusting them as a formula. So that is kind of one of the reasons why it might be not as convincing, because why, given this is true, this is true? Well, it is the theorem which I'm not going to prove here. Okay. So this one in the math side of mathematical analysis, this is called the Fourier transform of my function fx, right? And this one is the inverse Fourier transform. Okay, so as you can see, right, you start with a function of x. There exists a transform operation where you transform this, it becomes a function of k, right? But if you just have the function of k, you can actually transform back to recover the fx, and that is the Plancher's theorem. And this is why the chicken and egg kind of thing, you can use it to go back and forth. So this is one way to determine the f of k. Right, so when you get f of k, then we know what happens at some arbitrary future time t. I guess not. I believe for physics it is an optional course, but it's not compulsory. So this is the most mathematical analysis we will be using here. Okay. So just to see how everything fits together, I guess we shall work out an example. Okay. So let's open the screen. Okay. So the reason why the wave function initially is given, right? Like this question, the initial wave function is given to you. I have a free particle initially located between here to here, with the initial wave function is constant from negative a to a, and is 0 otherwise. So this is at time 0, right? So it's at time 0, and then at some later time t in the future, what is going to happen? So that is this is a typical scenario. This is how our solution works. Okay, so let's try to solve this particular question. This is example 3. What was it? 3.2.2. Okay, so let's solve example 3.2.2. Okay, so we got a free particle. Initial wave function is given by, well, my f of x is supposed to be my wave function at time 0, and it is a when my x is here to here, and it is 0 otherwise. Okay, so just to help us imagine, I shall draw it, but it's pretty clear, I hope. Right, so it's only a from here to here, so it's 0 otherwise. So that means it's 0 most of the time here, and then it goes to the height a over here, and then like this. So there is a a. So the first thing that we might want to do every time when we encounter a wave function is we will try to make sure it is normalized. So first, normalize to fix a, right? So that means 1 is supposed to be the integral from infinity to infinity dx psi square must be equals to 1. So this is integral from so my function is actually 0 most of the time, except is from negative a to a, right? And from its negative a to a, it just modulus a squared dx. So what you have is just 2a, right? So 2a mod a squared. So I can choose a to be a real number. It is going to be 1 over square root of 2a. Okay, so this is one way to there is one choice that will make sure the area under the square of this graph is going to be 1. Okay, so yeah, so I have chosen this already. Then I have found my initial wave function. So how to get my solution at a later time t? So in order to get a later time t, I need to determine fk, right? And how to determine fk? I do the inverse Fourier transform. So to determine fk, finding fk, we do the inverse or forward? Inverse Fourier transform of the initial wave function. Fourier transform of the initial wave function. Okay, so this is how we find the fk. So fk is the Fourier transform formula is doing this, right? And then I integrate this with respect to dx, and then my f of x, and then this is e to the negative, I already forgot. Fk is a negative ikx, right? No positive. Okay. So yeah, so just perform this calculation, and my fx was given by what? Is given by this. So my integral is 0, my function is 0 except from here to here. So this is actually 1 over 2 pi integral from minus a to a, and then my fx is just a, and I have found a to be 1 over square root 2a, and I just need to integrate negative ikx. Okay, so now you can see we can simplify stuff a little bit. Square root 2 times square root 2 gets a 2. Root pi times root a outside, these are constants, and I'm integrating e to the ikx. So if I integrate e to the ikx, I get negative 1 over ik e to the ikx, and then the limit is from negative a to a, right? Then let's perform this. Well, I got 1 over 2 root pi, okay, and then I got negative 1 over ik, and then if I plug in, the limit is e minus ika minus e positive ika. I will absorb the minus sign, so I got 2 pi a root 1 over ik. Absorbing the minus sign, it will just flip this, so I got ika minus e minus ika, right? And this is a familiar solution, right? This one, if I use the Euler's formula, it is equals to 2i sine of ka. So this I will cancel with this I, this 2 will cancel with this 2. So my f of k, I have found the f of k. So my, is it too bright? Found my f of k is just sine ka divided by the remaining factor. Okay, so this is pi a is always a constant, but the k is the, yeah, it's a function of k, right? So it's ka, k is the variable here, so it's got this. Okay, so this is how we have found the fk. by doing the Fourier transform. Okay. Okay. So I will answer your question. It sounds like interesting question, so I'm gonna get back to this soon. But I guess since we are doing this halfway, we get the full solution. We need to finish off the full solution, right? So I found the FK. The full solution is this full formula over here, right? So the full solution is psi x t is 1 over 2 pi square root integral from infinity to infinity with respect to dk of fk e to the I kx minus omega t, right? So yes, just now we have figured out this fk. I'm going to plug this into here, and the constant I will take it outside. So root pi and root pi comes out as pi, root a and 2, so it's just square root 2a. The k is a variable, so I should keep it inside the integral. Okay, and then it's just sine ka over k e to the I kx minus omega t. So that is as far as I can go, because we can't actually calculate this integral using our standard old school methods. We are going to need a computer to evaluate this integral. But just to show us the flavor of the results, right? Suppose we do have a computer that can do this. The result is let's go to the next page. I will draw this. So what is happening here is we can't calculate this by hand, but we can ask the computer to plot the graph at different t, right? So ask computer to plot the function at different t. For various t. Okay, so I'm plotting the graph of psi xt. Let's start at t0. So the t0 was it was the same initial condition. This is the given, right? Something like this. Okay, so this is time equals to 0, and then later at later is going to be like this. So previously was this. So let's copy this. Okay. So it's going to be like this. Let's try to draw as best as I can. And then later it's going to be something like this. So later t, even later t. Right, so this is as time increases. We see that the wave function spreads out. Okay, so this is it's not very satisfying because we haven't really done this by hand. We need a computer, but this one at least I'm showing you what is happening in the physics. So if I have a particle that is initially, that is initially between minus a to a, right? But if you just leave it alone for a while, and if you don't observe it for a while, it's a free particle, there is no force. So if you observe it later, you stop being sure where it's going to be, right? So the probability of finding that could be like spread out. So the wave function spread out, the probability of finding it at a different place later and later, the longer you wait, the less sure you are of its position. This is what happens for this particular initial condition. Okay. Yeah. So this is the example that we have here. So I guess it's 10 o'clock. Let me address some question before we rest. So this one, K1, K3, yes, it is a superposition of different particle behavior. Okay, the way to say this is the superposition is actually both are correct, like both meanings are correct. The particle wave function is given, so let's say we are talking about a particle of mass m, right? And all these are different possible wavelengths of the particle of mass m. So this k, well, this k is by the de Broglie formula. By the de Broglie formula, we can relate this to the momentum. So the superposition is the superposition of different states of momentum of a single particle. Okay, so let's imagine they are the single particle, and then these are superpositions of different momentums, right? Because a single particle can have momentum, this momentum, or whatever possible momentums. We don't know. So these are the superposition, right? It's the same story for the cat. A dead cat or a live cat, we are talking about the same cat, right? Whether it's dead or alive, we don't know what it's doing. So hope that makes sense. You're talking about analysis, right? Yeah. Math student probably doing the analysis. I don't know this semester or next semester. Why fx 1 over root a is because of the normalization, right? Because the big F of x is the wave function at time 0. So this is the wave function at time 0. And the area under the graph square must be 1. So this is why it must be square root 2a. Right? Because we are normalizing. Wave function must be normalized. Right? Yeah, this one you believe this, right? The area under the graph square must be 1. Okay? So I hope that makes sense. Yes, that's a simple. I mean, I took so long to explain, but it just means this, all the possible case for the particle, like the cat, dead or alive. So let's take a 10-minute break, and when we come back at 10:13, we will have some presentation, okay? Yeah, so let's take a 10-minute break, and I will stop the recording, and we come back later. But for now, let me start the recording here. And let us go to adjust brightness. Let us continue the story about the free particle. Okay, so now that we have solved at least 2 examples of the Schrödinger equation, right? The infinite square well and the free particle. So we notice that there are some similarities and differences between the 2 situations, but the huge difference that we have found is that for the free particle, right, what was the energy of the free particle? So the energy of the free particle is we have found this, right? E is h bar square k square 2m, and then there is no constraint on k. So k can be any number, well, any real number, because energy must be a real number, right? Energy must be positive, in fact. So that means k can have continuous value. Okay. Then remember what was the energy of particles in the infinite square well. Okay, what was it? I don't remember. Let me see. It is pi square h bar square n square over 2m a square. Right? So the thing is that n is an integer. And if I convert this back to k, k was n pi over a. Right? So it must be integer. So the k is constrained to take fixed numbers. So k can be pi over a, 2 pi over a, 3 pi over a. Okay, so that means they are discrete, right? So that means k can have discrete. Okay, so this is why, you know, when we are doing the free particle, when we do this calculation, right, we integrate over dk from minus infinity to infinity, because k can be anything. But over here, right, when we are doing the superposition, you are summing over all the possible k, which is actually summing over all the possible n, right? So k depends on n. So I can express n is equals to, yeah, you get what I mean, right? So it's a summation of discrete values. So this is the huge difference between the two cases. When we said that energy can be quantized, well, it's not always true for every situation. Energy is quantized for the square well, but energy is continuous, is not quantized. It can take any number for the free particle. So we will see why sometimes it is quantized and sometimes it is discrete as well. So let me discuss this a little bit further by comparing the differences. Okay, so when we are doing here, right, what we are having here is we got the Fourier transform. Fourier transform, and over here we got the Fourier series. Okay, so I would just want to mention very briefly the differences between Fourier series and then the Fourier transform. Okay, so Fourier series, we have shown that this happens is because my values of k are discrete. Over here, my values of k are continuous. Okay, and so let's compare and contrast our two calculations that we just did. So this is a quick summary of what we just did. I will just recap again. Previously, we did the infinite square well, right? Infinite square well, and today we did the free particle. Okay, so when we did the infinite square well, the first thing that we did in both cases, we were solving the time-independent Schrödinger equation to find the eigenstates of H. Right? So for the infinite square well, we have found them. It was square root 2 over a sine k n x, right? And then just now I just told you k is n pi over a, and then that will give me the energy of E equals to pi square n h square n square over 2m a square. So all these are discrete, right? So the k are discrete, and on this side, right, when we were doing the free particle case, we have solved the Schrödinger equation. We have found the eigenstates of H. So the eigenstates of H, without the time dependent part, it was EIKX, right? We multiply the time part, you get the minus omega t. Okay, so we have found this, and we have found my k to be square root of 2me over h bar, and the E is just h bar square k square over 2m. And as I have mentioned just now, we have no other information to constrain the values of k. The wave function was not normalized, so the way we did normalizing was superposition all the different k. It still doesn't limit the possibilities of k. So here k can take any values. Okay, so this was our solution that we have. And then one thing that I should probably emphasize a bit more, because in modern physics, I guess everyone solved this and stop here and interpret the solution. But now that we have learned the postulates of quantum mechanics and also understand what is the meaning of the time independent, is that these are just eigenstates of H. But in general, we can do superposition to create any new general solution. So that was what we did in step 2, right? The general solution is a superposition using the allowed values of k. So here the allowed values of k are here. For free particle, k is anything is allowed. So, but for the case of the infinite square well, the time dependent, firstly the time dependent solution, right? So the psi of kxt for a single allowed k, it was e to the minus IEN. The En was given here, t over h bar, and then the psi n was found here. So the general solution is a superposition of all the n and then coefficient e to the IEN t over h bar psi x, right, of n. Okay, so we have kind of done this maybe a bit briefly when we are doing the infinite square well, but the important one is, yeah, these are eigenstates, but other combinations are also possible. So we can do things like this. Okay, so this is the superposition, and then just now we have found the, for a single k, right, for a single k, my solution was EIE t over h bar psi x, and we have calculated this to be e to the I kx minus omega t, right? The details were just now, so I don't want to repeat this, but the general solution was superposition of all the allowed k. It was 1 over 2 pi, the square root of integral infinity to infinity dk, and then fk e to the I kx minus omega t. Okay, so one is a discrete sum, one is a integral. Okay, and this is where the differences between the Fourier series and Fourier transform comes in. So how do we when we write this, right, so this one we need to be it needs to be determined, and here it is determined by the initial wave function. So same story here, it is also determined by the initial wave function. Okay, so that's why in the third step in solving the Schrödinger equation, we look at the initial wave function at time t equals to 0, right? So my wave function f of x is the wave function at time 0. We didn't really do this here because there was not a need lah, but if we put this in, it is a summation of the coefficient of psi n of x over here, and then on this side we have done this just now, right? So just now was f of x is the psi at time 0, and this is the Fourier transform of fk, right? So it's infinite dk fk e to the ikx. So this is a inverse Fourier transform. Okay, so I'm just like recapping everything and writing everything side by side, so you can see the connection between one and the other. Okay, so one last thing to I should just say that this is a Fourier series. This is it is an inverse Fourier transform. So correct me if I'm wrong. When you guys were taking calculus 2, you have only learned Fourier series, right? But did you touch on Fourier transform? I don't think you did, right? But here we have to touch it. And Prof. Ong also told me that he did mention Fourier transform in modern physics to derive the uncertainty principle, which we will do it again here also. But in any case, right, we got these two situations. No touch, huh? Xiongshi introduced a bit. Okay, a bit only, right? But Fourier series there's a lot more things, a lot more interesting things to cover. But in any case, right, what we have found is the psi k, which was e to the minus I e n t over h bar sine k n x. These are stationary states. Okay, but generally the full solution will evolve over time. Okay, so what do I mean by stationary states? These do not evolve over time. If you calculate the probability density function, the PDF, right, is the sine function square. So sine function square always remains the same, right? Eigenstates of Hamiltonian are stationary states. But if you do an arbitrary superposition, you might get a function that will be evolving over time. Yes, we did not do this over here because it involves a lot more calculation, but we have done this in the example just now, right? So what we have found was the solution of eikx minus omega t are stationary states, but they are also not normalizable. But the full wave function, what was it? 1 over 2 pi integral dk fk e I kx minus omega t will evolve over time. Right? The example that we have just seen was, yeah, so initially we got this situation, right? And then we got this, and then it will become this, something like this. It's very hard to draw, but if you have the computer to plot this graph, this is what you would get. Okay, so yeah, so this is a compare and contrast between the two situations. So I think we are almost running out of time already. Yes, right. So yeah, I think that is what he meant by the mathematical analysis. So I don't know if the math students are taking math analysis or have they taken already, but it is a very interesting story. So previously I shared the 3 blue 1 brown video. Like there's a lot of things you can do using Fourier series and the Fourier transform. It's 2 minutes left, so I don't think I should start talking about this. I guess I should touch upon this a little bit, right? So how come does the infinite square has discrete k, and how come the free particle has continuous k? Because these are two categories of states. Firstly is the bound states. Okay. So the bound states it is defined by it depends on the energy of the particle. Okay. So the bound state usually, right, it is happening is that my potential energy is something like this, and then my energy is somewhere over here. Okay. So as you can see, right, if it's a Newtonian mechanics, the particle will be trapped between here to here. Okay, but the definition of the bound state is that if I go x to infinity, for large x, the energy is less than the potential energy. So the energy is less than the limit of x to plus and minus infinity of my potential energy. So you see over here, V is greater than E, V is greater than E. So in this case, usually, in this case, the k and therefore energy, the allowed, is quantized. Quantized means discrete. Okay, so these are the bound states situation. And then the other case is what we call the scattering states. So scattering state is like maybe, you know, you got something like this. It could be this type of situation, or maybe, yeah, something like this. As you can see, right, energy is higher than the potential energy. So the energy here is greater than the limit of x to plus and minus infinity of my potential energy. So usually for scattering states, the k and therefore E can be continuous. Right? In other words, no quantization. Okay. So the example of the scattering state was the free particle. Right? Because free particle is the potential energy 0 and E is always some positive number. And we have found that the K is continuous. And then over here we got the infinite square well. Because between 0 to A, the potential is 0, but anywhere else the V is infinity, so obviously higher than the energy itself. So the infinite square well is the case where the K and the energy are quantized. Okay, so we have these two situations, bound states and scattering states. So we categorize our system into two types. Okay. So yeah, so I think that should be all for now. We are running out of time, right? It's 10:52 already. So yeah, so we have in this chapter I will solve one more example of the potential. So we shall do that on the Thursday. And yes, that is the delta function potential, and that is one example where you can either have a bound state or a scattering state. So we're going to do both cases. And scattering state is going to be quite interesting if you are interested in quantum tunneling and things like that. So that is where the scattering states, that is where it comes in, right? The quantum tunneling will be here, right? This is like tunneling example. Okay, so yeah, I think that's all for today. We shall continue this scattering state system on Thursday. Okay, so yeah, thanks again for those who have presented today. It's always nice to see how you guys present, because different people come up with different ways to present the answer, and this is how we come up with creative ways. Presentation is like an art, you know, you need some creativity to convey information to an audience, and this is quite fun, at least for me. In any case, let me stop the recording.